Bismillahirrahmanirrahim. Diode models are very crucial for the design, analysis, simulation, and understanding of circuits that use diodes. And they contributed significantly to the efficiency and reliability of electronic circuits exist. In literature, many diodes models are available, but many of them are related to the specific type of diode, for example, solar cell, LED, laser diode, or some specific condition, very high frequency, very low temperature, etc. But very few general purpose diode models are reported efficiently. Here are some common diode models we will discuss, such as ideal diode model, piecewise linear diode model, Shockley diode. These models are the most common diode model, in other words, textbook model. We will discuss each of them in little detail at different points. First of all, we discuss about ideal diode model, which is a simplified representation of diode used primarily for basic circuit analysis. Here are the key characteristics and aspects of ideal diode. The characteristic of ideal diode model is divided into two behaviors. One is forward bias behavior, another is reverse bias behavior. In forward bias behavior, when diode is forward bias, positive voltage is applied to the anode relative to the cathode. It is considered a perfect conductor in forward bias. So therefore, the voltage drop across the diode is assumed to be zero. In other words, Vd is equal to zero. The current passing through the ideal diode can be any positive value and theoretically infinite current passing through the diode as long as the diode is in forward biased. In reverse bias behavior, when the diode is reverse biased, negative voltage applied to the anode relative to the cathode, it acts as a perfect insulator. And diode behave like an open switch. In reverse bias, the current passing through the diode is zero. In other words, ID is equal to zero. The main drawback of the ideal diode model is that this model does not account for the breakdown phenomenon, which is the most important and always occurring real diodes. The ideal diode model, as discussed above, simplified representation of diode behavior, but it has very serious limitations. One of them is that no reverse current. In the ideal diode model, the diode is assumed to have a zero reverse current. When reverse biased, which is not true in real diode. Real diode exhibit a small reverse leakage current. Another limitation is zero forward drop voltage. The ideal diode conduct with no voltage drop in the forward direction. In reality, there is a forward voltage drop, typically around zero point 0.7 volt for silicon and zero point 0.3 volt for germanium diode, and gallium arsenide close to 1 volt. That affects efficiency and power dissipation. Another important limitation is infinite resistance in reverse bias. An ideal diode is assumed to have infinite resistance in reverse bias, whereas real diodes have a finite reverse breakdown voltage and can conduct a significant current in this voltage is acceptable. Temperature dependence. The ideal diode model does not account for the temperature effect. In real diode, parameters like forward bias, voltage drop, threshold voltage, reverse voltage, saturation voltage, ideality factor, all these can vary with temperature. Dynamic resistance. The ideal diode does not consider the dynamic, in other words, small signal resistance of the diode. It can affect circuit behavior, especially in high frequency applications. Fastness effect. The ideal diode ignores junction capacitance, which can impact the diode's characteristic time and frequency. Mostly are required in high-speed electronics applications. Non-ideal switching behavior. In practical circuits, diodes have finite switching time, and can ideal model does not account for the delay during turn on and turn off. These limitations mean that while the ideal diode is used for basic analysis and understanding, more comprehensive models such as Shockley model are needed for accurate simulation and analysis in real-world applications. The ideal diode model, despite its limitations, is still useful in various applications and scenarios, particularly for first approximation of circuit analysis. The ideal diode model is useful for simplifying the analysis of complex diode-based electronic circuits. Another important application, a real application of ideal diode model, is conceptual understanding. It serves as a foundation for more complex diode behavior and models. The ideal diode model provides a straightforward way to analyze circuit involving diode, making it a valuable tool for basic electronic design and simulation. However, it should be complemented with more detailed model for precise applications.